Alright, welcome back to ECE382, the moment you've all been waiting for. Module 4, Part 2. I know, left you on a cliffhanger last time. Alright, today we're talking about the design using C programming, or just design in general for software design. So one of the key things that we like to teach in this class, or anytime we're working with hardware or software in that sense, is modular design. So modular design is basically kind of this idea that you think of a certain system and you design that system separately. For this robotics system, it's quite easy to think of it in a modular design aspect. So you have your motors, that could be one design component. You have your IR sensors, distance sensors, that can be one design component. Your line sensors, your bump sensors, your brains that's controlling all that. All of those are different designs, and we can use modular design to help us to just kind of have nice, concise code that will not be too confusing, and then we can reuse different parts. So if we develop one part, say the bump sensors in a certain part of the lab, certain part of the course, then we can use those down the road. When you get into the real world, modular design helps a lot when you're working with big teams. One person might be working on one portion of the project while another person might be working on a whole different part. So modular design is key design method, and I highly recommend whenever you code or whenever you work on some of these more complex systems, you think of modular design. All right. So let's take a look at what some things that we should think about when we come to system design. So current state. So basically, when we think about the state, we want to list state parameters. So for our robot, that could mean, what's the state of our bumps? Are they on, off? Is there a bump? What's the state of our motors, the state of our line sensors. So you think of all these components, and you want to just kind of think of the states. What's our current action? Are we, driving forward? Are we turning? And once we have all of these different parameters defined and listed, then we can really think about our state and, yes, what our state transition might be. So we saw that in 281. We have our states, state transition diagram. We're going to get back into all of that again later, just to kind of reiterate the importance of state transitions. And so if I'm in a current state, what's going to be my next state? So if I'm driving down the road, my bump sensors don't see anything, but my distance sensors see a wall, my motors are going forward, my line sensors are okay, and there's nothing to the left of me. So my current state is, hey, there's open left turn, and then I'm going to now do my action dependent on what that state is, and that might be turn left. Other things we have to think about, what's the initial state? So that might be, motors are not running. We look at the IR sensors and we determine what are we going to do next. So that's maybe our initial state. What information do we need? So this is list the input data. So that includes your distance sensors, all those different things. List the output data. So that's probably, for our example here, is going to be signals to the motors. And then actions we can do. We can drive straight, we can turn left, we can turn right. And then what is to find the ultimate goal, what is our ending state? So if you do all of those, six different steps and kind of pre-process thinking of designing a system, It makes it a lot easier, and then we can think about how do we take that and create modular or modules for that. So how do we break this up into smaller problems? And that's the key thing with system design, especially when we start talking about hardwares or embedded systems. We definitely need to think about our input data and our output data. What can we do? How do we get from one state to the next? And then what's our ultimate goal? Which for us, the robot getting to the end of the maze, input data, obviously all of our sensor data, output data, it's going to be our motors. And then, we can turn, we can go, make small adjustments, all these different things we can do. So the idea of successive refinement is basically this idea, again, of this modular design. So we start with a task. So let's say, for example, we want to drive between two walls, bump into the end wall, and stop. So not super complex system, it's pretty straightforward. We're going to, we have two walls on the left and right. We're going to use our distance sensors to drive between them so we're not bumping into the walls. We're going to go straight towards a dead end. We're going to hit that wall and we're going to stop. So now if we want to decompose that into simpler subtasks, we have a drive task. We have a distance sensors that we need to process the data. We have our bump sensor. Then we have our controller, which is going to take the input from all of those different, those two different sensors, the distance sensors and the bump sensors, and it's going to output our drive task, or kind of do our driving. And so that now we've decomposed this to 4 simpler tasks. So now you could do this if it was a team project. One person might take drive, one person would take distance sensors, bump sensor, and controller. You just kind of agree on, hey, these are the inputs I'm expecting, here's the outputs I'll need, etc., etc., and you just go and you can decompose it in modular design and then come back together, and it probably won't work. So then you debug, figure it out, and go from there. But that's kind of this successive refinement. So we're going to start with our big requirements, break that down into simpler tasks. You do need to make some design decisions. So are we going to use interrupts? Are we going to use polling? All these things you don't really know what they mean yet, but just some things you have to agree on. So for example, we can use interrupts to control the bump. So instead of me as the controller constantly going out and saying, what's the bump sensors doing? What are the bump sensors doing? What are the bump sensors doing? What we would do instead is in the bump sensor task, the bump sensors, as soon as a bump happened, it would have to initiate a interrupt, and then the controller, all it would be doing is, hey, I'm doing my normal processing, and then an interrupt occurs, and then I know, okay, my bump sensors have been updated, and now I need to do something. And then the subtasks we need to implement, test, and document each of those tasks. So we take drive, we implement it, we test it. We can test it without the distance sensors, without the bump sensor, without controller. We just want to make sure the two motors go forward, left, right, backwards, etc. Then we'll test, then we'll document that. So we won't have to write a lot of reports in this course, but in other courses, you would take that and then document that drive. Then you document distance sensors. Then you do the same thing, bump sensors and controller. And then we bring that all together. We can copy and paste pieces of document from each of those into our bigger system, which is driving between two walls, bump into the end wall, and stop. And so that's when we combine all that to build our system. So those two, between the modular design and the successive refinement, those are two software design methods I want you guys to think about and use. I use them all the time. And if you are in the ECE department, we have a class called ECE 495, Fundamentals of Robotics Research. And we use this tool, I don't know what happened there, whatever, ECE 495, we use this tool called the Robotics Operating System. ROS, and you might have heard the department us talking about it, Colonel Neff, myself, or you might have some of your classmates or yourself working in 495 right now. But one of the key things ROS provides us is this successive refinement in modular design. And so if you're in that 495 class, you're going to hear this a ton, and you're going to get tired of it, but it is so powerful. All right, let's get a little bit more into C coding specifics. So in C, in your starter files, you'll see this include folder. So inc folder, this folder will include .c files and .h files. A header file is what allows us to describe the component. So you might see a bump.h or a I think it's reflectance, which is the line sensors .h. And what that .h file does, it describes what the component can do. So it lists prototypes, and you might remember this from CompSci 210 for public functions. So what functions does the bump.c file have, and how can we use those? So it provides comments on what it does and how to use it. Code to make it load. And then whatever shared structure is it's going to provide to other components. So those constants we saw before, you could define the names of those constants if you want to use those in a different file, stuff like that. So what is not in a header file, though, are the function definitions. So that's actually, what does this is the actual code. Variables. And so when I say variables, the key thing to note here is you can use like enumerated types and constants and have those defined in a header file so that then the C files can use those. So constants can be used in header files, but variables, so that's where we say we don't like those external global variables. We don't want those we just don't want to do those. And then anything private does not go in there. So anything that's just local to the .c file, we're not going to include in the .h file. So what is in a code file? So this is where we actually start implementing the functions. Public functions. Everything on private functions are in the C code. This is where we'll put our variables, and then comments on how it works, tested, and what can be changed. So, for example, in here, in our header file, we might have int int bump read, and then it has no inputs, and that's just your prototype for a public function bump read. And then in the code file, is where, whoops, those are supposed to be, you would actually put that void in there. That's where you would actually write, P4 in, or bump equals, etc., etc. And then you would have your comments, reads bump sensors, and you can have a comment here, function to read sensors, etc., etc. So I encourage you to open up the include folder, look at the .c and .h files that are in there. Those will allow you to kind of get an idea of what stuffs you can use. And then we will be creating and editing .h files and .c files throughout this course. And it's just important to know what can go in and what shouldn't go in. All right, that's it for this video. I'm going to break up these two videos just to allow you guys to not have to sit there and watch a 30-minute video. But this next video should be pretty short, and watch both. Well, after you finish watching this one, watch part 3 as well, and that will get you prepared for the next lesson.